Our project is to compare performances of different gradient descent algorithms using Ames Housing Dataset. We find our dataset on Kaggle, and this is the Kaggle page with more information about the dataset. And the original dataset has 79 features describing different aspects of residential home at Ames, Iowa. And you can see some of the features listed here. And the task is to predict the sale price of a home with a set of given features. We first read in the first 500 records from the dataset, and because we are using linear regression model, we remove all the features that are not numerical variables. We also check if there's any missing value, and you can see here there are 3 features has missing value. So we remove the records that has missing value for these 3 features. We also drop the ID because it's not a very meaningful feature to be used in the prediction model. Next, we run Pearson correlation for features against each other, and the primary one we are interested in is the correlation with sale price. You can see some of the feature here has a pretty high correlation, and some of the feature here has pretty low correlation. So we retain all the features that has at least 0.5 correlation with sale price, and we are left with 11 features. And before running any type of gradient descent, we normalize our data, subtract the data point by mean, and divide it by standard deviation. This is the implementation for the 4 different gradient descent algorithms we use in our project. This is the standard gradient descent, and this is the momentum accelerated gradient descent. And the last 2 are normalized gradient descent with the component-wise version and also with the fully normalized version. And so this figure 1 is our hypothesis for the experiments we did. We think standard gradient descent will perform the worst among all 4 techniques, because the minimization process of standard gradient descent often are slowed down due to the vanishing behavior near stationary points, and also the zigzagging behavior along the long narrow valleys. And the momentum accelerated gradient descent helps to deal with the zigzagging behavior, and the normalized version of gradient descent is often used to deal with the vanishing behavior. But surprisingly, this figure is the actual result we get, and here we use the biggest possible alpha value for each run, and we can see here standard gradient descent actually outperform the other 3 algorithms. And the reason behind our findings could be we have pre-processed our data through normalization, and the data has relatively large gradient. So using just gradient descent is enough to efficiently minimize the function without getting stuck anywhere, and the large gradient value allows standard gradient descent to actually converge faster than other techniques. So I think the performance of each gradient descent algorithm really depends on the data people use, and in some cases, like here, the data quality is relatively good, and it is enough for a standard gradient descent to be used to find the best ways. for the model very quickly.